All right, let's take a look at this packet really quick. Some pretty simple math. Of course, I don't have a calculator, so let's grab a calculator. All right. A lot of information here. So try to hold on and pay attention. I'm gonna kind of quickly tell you what you really need to notice. Now, you should read this on your own. I'm not gonna read the whole thing to you, but I guess right out of the gate, that first sentence is pretty important about mechanical waves. They transmit energy without displacing the mass overall, right? Like when a wave vibrates a spring, the wave vibrates it, but then it settles through and the energy goes from one side to the other, right? So like some of it reflects back, of course, but I transmit energy from one side to the other side of the medium, right? Think about the people shaking the spring in class. Call that wave propagation, so on and so forth. So from the demonstrations, what variables affected the speed with which a wave pulse energy traveled through a medium? And for my demonstrations, is really just the tension in the spring. And the spring is just a model for any medium, right? So I suppose that kind of goes with the density, right? Density / bonding of a material. So a solid is bonded more strongly than a liquid is bonded more strongly than a gas. Sound travels at 330 meters per second through air. Sound travels much quicker. I don't know the number off the top of my head through a solid or a liquid because the molecules are close together, right? Like literally, you could think of like the molecules of gas being separated. So when the wave hits this one has to hit this one, which then hits this one, which then hits this one. Well, if they're closer together, that energy can cascade through the material a lot quicker. What happens to the wave pulse when it hits a boundary with a different material? Well, some reflects. We saw that, right? And some transmits. Right? So some of it went into the person holding the spring, some of it bounced back at the person on the other side. But also when it reflects, the pulse / wave inverts, right? So if it comes in as a hump, right, when it reflects, it leaves as a dip. It turns itself over as it hits. Mechanical wave interference, we demonstrated this with the slinky. When waves overlap, they end up constructively interfering. So if this one lines up with this one, right, you have that plus that, two of them add together to make one big amplitude. It's almost like they have to like stack them up. Like that would be 1, 0, and this would be 0, 0, so they add up to 0, but then here's 1/2, so they add up in that way. If two waves are the same shape but then invert each other as it passes through, the string just kind of stays flat. But then once they're done interfering, things just keep moving on their merry way. They pass through each other. You kind of track the middle of it, right? They cancel each other out. The middle of it doesn't move, and so on. Now, these ones we did in class, this plus this equals one taller one. It will be the height of two of them added together while they overlap. This one here you end up with the base, but then with like a peak for the smaller one right on top of it. All right, now these aren't perfect. This one here ends up like this, but with a chunk taken out of it. Now, again, I'm not doing a super great job here. That should be the same on either side. And then this one ends up like a house, looking like a house. So you have the original waveform plus the triangle shape on top of it. Those are all constructive or destructive. This one, I guess, destructive because it's got a negative amplitude, so that takes out some of the energy as it passes, but then it just keeps moving. We got some fancy definitions here. Superposition principle. This is super important here. Transverse waves, longitudinal waves, super important. All right. Transverse waves, as the wave travels through the medium goes up and down, up and down. Compressional, the medium vibrates forwards and backwards. All right, so the compressional, you have like these pressure things. Those are your peaks and troughs and so on. We're going to see in the next page or in a minute, we can use the wavefront model for these things. You really got to know that sound is probably the most important compression wave that we talk about. Pretty much everything else is transverse. Periodic waves, that just means you put pulses of energy into a medium at a set frequency and you get a periodic wave, right? And those can come in all shapes, weird patterns, but as long as it's a repeating pattern where we see this repeating pattern, it's periodic, right? If there's not a repeating pattern, it's not periodic. All right, so this is probably one of the most important parts. I'm going to give you the symbol, the unit, and a little diagram. So over here, I'll make a diagram of a wave and illustrate as many of them as I can. All right, I'll go one more. So that's a wave. Let's say it's moving that way. That's what the arrow's kind of showing us, right? Amplitude, the symbol is A. The unit is meters. It's the height of a crest or a trough. And it's referenced from 0, right? This would be the medium just when it's flat, then the wave. So that would be a positive amplitude. Excuse me, that would be a negative amplitude. All right, this pen is not my favorite. Smudgy. Let me grab something different here. All right, I've got a blue gel pen now, so whatever. All right, wavelength, the symbol is a lambda. Also, it's a measurement of meters. It's the distance of one complete cycle. So lots of ways to draw wavelength. I'm gonna draw it over here. That would be one wavelength from there to there. So literally whatever that length of the wave is. In the class, we looked at waves that were 5 meters, 10 meters in wavelength, depending on how we shook the spring. It all depends on the frequency we shake the material at and how fast it can move through the material, right? So we'll see that in a second. Frequency, units are hertz. All right, so we gotta talk about that real quick. A hertz, the symbol is an Hz, and an Hz is a 1/2. Now that's a bit confusing. It's really like a count per second or a number per second. It's these cycles of vibration each second. So if something makes one complete vibration in 1 second, meaning like takes 1 second for a wave pulse to fully move one wavelength, then the frequency would be 1 hertz. I don't have a way to illustrate that. Or you can think of it like, okay, how many crests are passing by a certain, like a thing every second, right? Like if you could time the number of crests passing right here, like you could stand there and count them, right? How many are passing each second? That would be frequency. So how many complete vibrations is it making per second is frequency. Period is in seconds. That's the time it takes for one complete cycle to happen. All right, how long does it take the spring to go up down and back up again, right? Or how long does it take a full wave to pass some point in the medium? And there's a relationship, period is 1 over frequency, and that's an equation that we have on our reference table. And I'll have to grab a reference table here. Hold on one second. We've got right there, period equals 1 over frequency. Okay? And then phase is the angular measurement, and this can be in degrees or radians. So just like a sine curve, right? I can redraw this one here. When you have a sine curve, right, the distance in degrees between the different components is, this is pi, right? Then the full width would be 2 pi, right? And then a half of a wavelength would be pi over 2, and so on, right? So phase is the distance in terms of angular measurement between parts of a wave. All right, the wave equation. So I was saying you can, the speed of a wave is its frequency times its wavelength. So let's just do this first part first. Show that multiplying frequency by wavelength gives units appropriate for velocity. So frequency I said was hertz, right? Times wavelength, which is in meters. However, what you got to realize, a hertz is a 1 over a second. So if we multiply those together, it's 1 over seconds times a meter. It gives us meters per second. Now, I didn't put the word cycles in here. Cycles is just a count, right? It's a certain number of things per second. Degrees per second is a frequency as well, it turns out. We call it angular frequency. But anyhow, that'll give us meters per second. And really, the thing is, we generate a wave at a certain frequency, and then its wavelength and its velocity then depend upon the medium, right? So really, it's the wavelength depends upon the medium that the wave is moving through. So an 80 hertz sound wave, so that's being generated by something oscillating 80 times a second. Travels through air at that speed. That's the speed of sound in air. Also on your reference table, they write it a little bit differently. And they give it to you right here. Speed of sound in air at STP, 3.31 times 10 to the second, which is 331. Most people just make it 330, whatever. What must its wavelength be? So V equals F lambda, 330 meters per second equals 80 hertz times lambda, or lambda equals 330 meters per second divided by 81 over seconds. Seconds are going to cancel there. We're going to end up with meters, so 330 divided by 80. Oops, not a natural log. 330 divided by 80 gives us 4.1 meters. So an 80 hertz sound wave, that's like a low bass note. Boom, real low. 4 meter wavelength. So the air is vibrating such that its wavelength is 4.1 meters. All right, we already mentioned this. Period is 1 over frequency. So to determine the period and wavelength of a 440 hertz sound wave traveling through that was that A note we talked about. So first of all, period is 1 over frequency. So period equals 1 over 440 hertz. So that's going to give us a time. So it would take the string 1 divided by 440. It would take 0.0023 seconds, or 2.3 milliseconds for one complete cycle. All right, and then the period and wavelength, I got to use the wave equation. So lambda equals V over F. I'm just taking the equation I learned up here, rearranging it. All right, lambda equals V over F. So the speed in air is 300, and I'll do the 31 on the reference table, 440 hertz. So we're going to get a wavelength here. 331 divided by 440 is about 0.75 meters. Now, A440 is a note that tends to ring out in certain rooms because its wavelength is 0.75 meters, so that's, but you can think of what a meter stick looks like, and rooms could easily be certain integer values of that causing resonance to occur. So given the following diagram, determine the phase between the points. So V and X. All right, V and X are pi, or pi radians, or 180 degrees. V and Y, okay. Got to add another 90 to that, so it looks like 270 degrees, or 3 pi over 2. So it'd be pi over 2, pi over 2, pi over 2, 3 pi over 2, and X and Y, that looks like pi over 2. 90 degrees, or 1 pi over 2. All right, very good. Phase, easy enough. No big deal. Wavefront model. So the wavefront model is just a way to draw waves from a two-dimensional top view perspective, right? So we represent crests in waves by lines, troughs as dashes. So when you drop something into water, right, a rock into water, the wave crests ripple out. They travel out, right? And then I suppose I can draw troughs between each one of those. Now, otherwise, you don't really have a way to draw a water wave happening in 2 dimensions without this wavefront model. Draw a sine wave with 4 complete cycles along the arrow below. Get rid of that part, okay? So, 4 complete sine waves. 1, have I left myself enough room? 2, 3, yeah, not bad, Harmon. 4. So, crests are gonna be lines. So I'm just kind of trying to line it up. And troughs are gonna be dotted lines, just in between the crests. Usually we don't even draw the dotted lines, but we'll see in class that, oh my gosh, I wasn't even on screen. We'll see in class that sometimes the troughs are useful. So we talked about this, diffraction. It turns out mechanical waves, they bend as they go through barriers or around objects, right? I showed you this in the water table. You got to remember this: narrow opening, more bending; lower frequency, more bending. That you got to remember. Something you absolutely have to memorize. Okay? That page is just memorization. Wave interference patterns. We talked about this in class. Just a demonstration. Basically, when you have 2 speakers creating sound, they send out these waves. Anywhere where the crests line up, we get peaks in the interference. There'll be a loud sound. And then where 2 troughs interference, we could also have a loud sound. But then where a crest and a trough meet, then they cancel each other out. So we got quiet spots. So as we walked around the room, we saw that we had these different areas of constructive and destructive interference. Now, that's just a quick demonstration for fun. Interesting to see. Energy transferred by an individual mechanical wave pulse is directly related to its amplitude. So for mechanical waves, the energy that a wave delivers is related to its amplitude, right? Think about a water wave hitting something, right? This one's got more energy, right? But when you do think about, like, okay, let's say I'm transferring this into a break wall or something, right? Waterways are splashing up on this wall, right? The total energy, internal energy buildup of the wall is going to depend on how many waves hit it. So a bunch of smaller waves hitting at a higher frequency more often can end up delivering as much energy as one big wave. But when we look at individual waves that are identical, whatever one has the bigger amplitude has more energy. So that's really what you got to focus on. We're not so much interested in how many wave crests are hitting. It's just, it's that. All right? You can look at that. Doppler effect. We have a Frisbee demonstration we did in class. When the source is moving towards you, when the source of sound moves towards you, the sound waves get compressed because They're getting shot out of something that's moving. So it moves through air at 330 meters per second. The speed that sound's moving at doesn't change no matter how fast this is moving, right? So if this is moving at 50 meters per second, right? The sound waves are traveling at you at 330 meters per second. All right, that's not going to change. But if this is going 50 meters per second, then each wave is going to be closer to the one in front of it and farther from the one behind it, right? So you get like this pressure front buildup of the waves. So you hear a higher pitch. If it's moving away from you, you hear a lower pitch. Now, if the object is accelerating or decelerating, so if it's speeding up, the pitch is going to go up. If it's slowing down, the pitch is going to go down. That's why I like on TV when a race car goes by the camera, it's not just like a constant pitch necessarily. Sometimes it can shift because of the angle at which the sound waves are hitting the people. So there's just a quick question. Let's say a fire truck accelerates from rest, passes you halfway through its acceleration. Describe the observed change of pitch as it accelerates towards you. So if it accelerates towards you, the pitch is getting higher. Right? As it passes next to you, you hear the true sound, right? So all of a sudden it's going to be high, getting higher, and then you hear the real sound, so it's going to probably drop really fast. Right? Because you're going to start hearing the true sound. As it was moving towards you, it was getting higher and higher and higher, like, and then, so it's going to get higher, and then as it passes you, you're going to hear the real frequency, so it's suddenly going to drop, and then as it accelerates away from you, it's going to get lower in pitch. And there's any number of videos online that can demonstrate that. So that's it for mechanical waves. Next will be sound, or electromagnetic waves.